I bring you Dr. Ramis Arbi. Dr. Arbi is a postdoctoral scholar in the Faculty of Engineering at McMaster University. During his PhD in engineering physics, he worked on the fabrication and characterization of designer nanoparticles for energy devices. Currently, his research with Nico Hildebrand in engineering physics looks at developing FRET-based optical sensing applications for biomarkers and environmental pollutants. Outside of the academy, Dr. Arbi rescues old computers and electronic equipment. His greatest rescue to date is a 20-year-old monochromator, I hope I said that correctly, and a 1986 Macintosh Plus, which he brought back to life. So please welcome the Dr. Frankenstein of electronics, Dr. Ramis Arbi.
Hello, everyone. Today, I'm going to be talking to you about detrimental heavy metals and where to find them. So heavy metals are bad. They're bad because they cause developmental issues. They can have reproductive issues. They can cause drastic effects on multiple systems, organ systems. And in fact, different environmental agencies, including Health Canada, have limits on how much of these heavy metals you can have in things like your drinking water. And they range from a millionth of a gram per liter to 1,000th of a gram per liter, which is very, very, very small amounts. And you may have heard about exposure to heavy metals through aquatic sources, where small animals are consumed by larger fish, and so on and so forth, till you accumulate these heavy metals till they reach humans. But that's not the only source of these heavy metals. You can get heavy metals in your drinking water, either from a lake, a river, an aquifer. And these are usually sourced from human activities such as mining, landfills, or agriculture, or from natural sources such as erosion. In fact, if you're living in the city of Hamilton, the city has an advisory that you may have lead in your tap water if you're living in an old enough house, or if there's lead plumbing along your service route. Canada by itself has 7 to 9% of the world's accessible fresh water. And respect, they have a multi-barrier approach to protecting these lakes and rivers and aquifers. In fact, if you're living in an urban city, you have free access to testing of your drinking water that is supplied to your house. But there are wells, there is groundwater, and that's how a lot of remote communities get their water. Sparse water treatment and sparse water testing result in underserved communities. And that's Canada with its resources and a lot of water. There are developing countries where this entire impact is compounded, especially so for underserved communities within developing countries. In fact, if you're living in Canada and getting your water through a groundwater supply, you're responsible for your own testing. That brings me to how you test these ions in water. You can use a variety of different techniques. I'm not going to go into the details, but they range from accurate, like very accurate, to not very accurate. And in the opposite direction, they range from accessible to least accessible. So you can either know exactly how much you have, but require a lab and trained personnel, or you can know ballpark how much you have, or at least how little you have, and you can do that at home. My research is trying to bridge this gap between accuracy and accessibility, and my champion in this battle are optodes, which use optical sensing, which is basically a mechanism in which you get a conversion of interaction of light and matter into a sort of quantifiable signal. In fact, if any of you are wearing smartwatches, that's exactly how your heart rate and oxygen sensors are measured. So that's what the green flashes are all about. A basic structure of an optode requires 3 parts. There's a sampling medium, sampling interface, which is the part that touches your thing being measured. There is a material exchange medium, which is how that analyte from your sample travels to the transducer, and the transducer is the brains of the operation. It's the thing that changes in response to an analyte. My transducer are these voltage-sensitive diodes, which respond in one of 2 ways. They either change in brightness or they change in color. While designing this device, there are a few considerations to think about. I want this device to be continuous. I want this to be able to measure things right now, instantaneously, not something that I drank yesterday or I was drinking 5 minutes ago. I need this to be robust. I don't want it to get destroyed just by putting it into water. And I need this to be chemically stable. So I need to be able to put it in different kinds of water. And also, I wanted to be specific. If I'm measuring lead, I want to measure lead, not magnesium, not zinc, lead. And so my device looks a bit like this. It's a wand with a little disc at the other end that you can see in pink. And it's wired using optical fibers to a photodetector and light source. And the pink disc at the other end is just made up of many, many small pixels, each of which are these polycarbonate stable pillars, which are dyed with this polymer, ormocil. And the signal from the dye in the ormocil is measured against the reference dye using the detector, and that's the signal that you're measuring, which is converted into a concentration. In fact, this dye is so porous that you can see a representation in, well, I made that. It's not an image. You can see a representation where gray is where the water would be, and the white is where the polymer is. This allows efficient exchange of the analyte between the water and your dye molecules, so change in pink can be very quickly measured. So my solution to this is using photostable, thermally stable, and chemically stable materials to make a device that has been tested with pH sensing, so changes in hydrogen ions due to acids and bases, which I'm trying to convert into changes in lead concentration because of hydrogen ions produced as a result of that interaction. And the dream is to turn this into a self-contained pen that can be used as a thermometer. Thank you.